All right, for today we're going to look at different types of solutions with our systems. Up until today we only saw one type, that was one solution. If you're trying to solve a 2x2 system of equations, what is the best way and fastest way and easiest way to go about it? You could use elimination, you could use substitution, but the easier method is graphing. So let's go ahead and graph this system right here. And based on this graph, what would be my solution? Zoom in.
Oh, no, that's 6. 6, 2.
Not 6, 2, but 2, 6.
2, 6.
Yeah, 2, 6. So it's where they intersect. So my one solution is going to be 2, 6. Now, there are other types of solutions. And one of them is a no solution. Let me show you how a no solution works out by hand. So for this set, looks like my best method will be the elimination method. So I'm going to multiply this bottom equation here by -3. So let me just distribute that -3 across. So -15x, that gives me a plus 15y and a plus 15. I'm going to add that to the other equation, 15x minus 15y equals 0. And let's see. Looks like my x is canceled to 0. My y is also canceled to 0, so this entire left side is a 0. And that equals 15 plus 0, which is 15. Now here's an expression. Is this true? Does 0 equals 15? No, this is false. So this is how you read a no solution based on algebra. When you get something weird like this, 0 equals 15. Now let's think about the graph for a second. Say you want to graph this. If my one solution is an intersecting point between the two lines, what do you think a no solution would look like? Where they do not intersect at all. If these two lines do not intersect, then these two lines are parallel. Very good. So let's go ahead and look at these two lines here. And I see, in fact, that they are parallel and they do not intersect whatsoever. So if you were to graph a system and you're trying to figure out the solution and you see something like this, you would put no solution. There's one more type, and that's infinite solutions. What if every value for x and y works for both equations? Again, I'm going to demonstrate by hand. So it looks like I need to multiply, I'll go with the top, by a -2. I'm going to use the elimination method. Let me distribute. That's -10x minus 14y equals -10. So let me add these two together. I get 0, 0. So the left side again here is 0. And on the right side I get 10 minus 10, which is 0. Now just because you see 0, don't go ahead and assume no solution. That happens a lot. I see an expression that says 0 equals 0. Is this true?
Yeah.
This is true. So if this expression is true, that means that's when you have an infinite number of solutions. Or you could say all real numbers. That's just really a value for x. Just say infinite solutions. Best way to go about it. Now, what do you think the graph looks like when two lines are equal at every single point?
Same one.
The same line. So let's go ahead and graph those two. So here's my first line, and look what happens when I add the second line. Goes right on top. So they are the same line. It's just that this second one is the first one multiplied by 2. 5 times 2 is 10x. 7y times 2 is 14y. 5 times 2 is 10. I just doubled it. So yes, if you're trying to graph and you see that the two lines are on top of one another, you would say it's infinite solutions. So there's the 3 types of answers you're going to get. Now we're not going to work too much by, if we have a 2x2, we just saw your best method is just to graph it. You cannot graph, at least not yet, Technology hasn't caught up. A 3x3, at least not the technology in the classroom. I do have pictures and I do have video to show you what a 3x3 looks like. Actually, I might be able to find this somewhere. Maybe I can bring them up. But let's just say you got to do this kind of by hand. We're actually going to use a calculator, but before we use a calculator, we need to turn this into a matrix. And we're going to use that matrix for the calculator. So for today, we're just going to learn how to turn a system into an augmented matrix, which looks like big old brackets here. And it's just going to be a set of numbers. The numbers I'm going to grab from the coefficients. So it's basically each row corresponds to each equation, but without the variables and without the operators. One thing we need to make sure that's important is that we line them up perfectly. So all my x needs to be in the same column, all of my y's, all of my z's, and the value that's on the other side of the equal. These could be switched around, but I suggest keeping it in alphabetical order. This, what's on the other side of the equals, has to be on the right-hand side, or our calculation that we're going to do later next week won't work. So, let's look at the first equation here, and I only want to grab the coefficients. So what number's in front of my x? 3. What number's in front of my y? 8. What number's in front of z? 2. And what's that constant there? -5. So notice this is the first row of my matrix here. It looks the exact same except for without the variables and the operators. So if that's my first row for the first equation, what numbers do you think I'm going to put here for the second row? 2, 5, -3, and 0. So again, make sure you actually pull out the negatives. If you see a -3, that -3 needs to go there. Very good. So the last row, here's my last equation. What numbers do I have in front?
1.
A 1, 2, -2, and -1. There you go. Here is my augmented matrix for this system, right here. Nothing new, nothing hard there. You're just pulling the numbers away. And then, like I said, next week we're going to use this to calculate the solution. One more. Let's turn this system here into a matrix, like so. What's going to be my first row of numbers? 1, 1, 3, and 0. What's my next row of numbers? 1, 3, 5, and 0. And my last row? 2.
No. Wait. 0.
This is my y row. Look at the y's. Do you have y's here? Nope. So make sure you make note of that. Any missing variables gets represented by a 0 within your matrix. Now I'm back on my 0, which is 4 and 1. So this had no y, which means I have to represent that as a 0. Like so.